Let us arrive at the grand canonical ensemble distribution by using the ensemble formalism. So if we have, let us consider an ensemble is nothing but a system of identical systems. Large number of identical systems can be called as an ensemble. So let us consider to have nm number of identical systems which are sharing a total amount of energy nm E bar, where this is the total energy shared by this nm identical system and sharing a total number of particles nm n bar. So this is the total number of particles. Now if nRs, let nr comma s defines the number of the system which are at a particular instant of time having a number of particles nr and energy es. So if nr be the number of systems possessing having nr number of particles and energy possessing energy es, then we can write, if nr be the number of the system, then the total number of systems would be obviously equal to summation over r comma s to be equal to nm. This is the first condition. The second would be nr comma s nr would be equal to nm n average or mean n summation over s, and nrs es is going to give us nm E average. So these are the three conditions which should be satisfied by the given ensemble, where you have certain number of particles which are varying and the energy to also vary, and we have certain number of particles for nrs as nr and the corresponding energy to be es. Okay. So our main objective, as was already there for canonical ensemble, the same motive will be also applied over here. Only thing is we are having a new system where even the number of the particles are also variable. So for such we have the distribution nr. This nr is one possible distribution, one possible system. There could be some other possible system having certain other number of particles and energy. Then what is the number of ways? Then this distribution nrs should depend on the number of the ways in which these particles are arranged. So the number of the ways in which this are arranged, number of ways in which, if I call for a given distribution as nrs, this should be nm factorial divided by multiplication of nrs, okay, factorial. So this distribution should depend on this and the distribution of nrs. So there are basically three conditions which again can be used for varying delta nrs. So here, from here you can get delta nrs to be equal to 0. From here you can get delta of nrs into nr r comma s to be 0. From here you can have delta n r comma s yes to be 0, and from here also you can take log of omega and then log of w, which under starting approximation would give you something like log of summation of nr, okay, s plus 1 delta nrs. So these three conditions along with this, they are going to give us a possible distribution function by using the method of Lagrange's indeterminate multiplier. You multiply this with alpha, this with beta, and then you can have a mathematical condition for the most probable distribution, to be something like nrs to be equal to e to the power minus alpha of nr minus beta of es and divided by summation over r comma s e to the power minus alpha nr minus beta es, where alpha and beta are the Lagrange's undetermined multiplier which are to be determined by using the thermodynamic considerations. Okay, so the most probable distribution is given by this n r comma s is equal to, and if we want to know the physical significance of the parameters, statistical quantities alpha, beta, then we need to know quite a few things. The first thing we need to remember is that the mean number of particles n bar is nothing but equal to summation over nr e to the power minus alpha nr minus beta es divided by summation of e to the power minus alpha nr minus beta es, which is basically nothing but equal to minus of del alpha of log natural of summation of e to the power minus alpha nr minus beta es. The same fashion we can even define the mean energy as equal to summation of es e to the power minus alpha nr minus beta es divided by summation of e to the power minus alpha nr minus beta es, which can be written as minus of del beta of log natural of summation of e to the power minus alpha nr minus beta es. So what we can see is that this particular parameter is of physical importance, which log natural summation e to the power, and according to Kramer he had defined this as the quantity which is called the Q potential. So let us assume the Q potential. Q potential is defined as Q is equal to log natural of summation of r comma s e to the power minus alpha nr minus beta es. Okay, and now if you want, you can see that this Q is a function of alpha, beta and es. So if one assumes that this Q is a function of alpha, beta and es, then one can write dq to be equal to del q by del alpha into d alpha plus del q by del beta into d beta plus del q del es into des. Now what is del q by del alpha? We can see that this is nothing but equal to q, and here also this is nothing but equal to q. So del q by del alpha is nothing but minus of this minus n average mean n. Similarly, del q by del beta is minus of e average d beta, and this is something which gives del q by del es to be equal to negative again. So es, so this is going to give us minus of beta, okay, del es. So 1 by summation e to the power minus alpha nr beta es, and differentiation of this, so that is going to give us e to the power minus of alpha nr beta es into des. Okay, so this is going to give us beta of ds. So what we can say is, now if I say that d of q plus n bar alpha plus e bar beta, okay, or we can write this. So this is nothing but equal to dq plus alpha dn bar plus n bar d alpha plus beta d bar plus e bar d beta. So if I want to write this, dq plus nd alpha, dq plus nd alpha plus e bar d beta, so that would be equal to alpha dn bar plus beta d bar, okay, and these two terms are there, dq plus nd alpha plus, and there remains another term which is equal to, so comparing these two we can write alpha dn and minus of beta summation of alpha nr beta es des by okay. So one can write this, and now if we want to have a physical significance of alpha and beta, then we need to remember the first law of thermodynamics, according to which we can write, okay, before going to the first law of thermodynamics, we can even take common from here, beta, taking common beta, so dE average plus alpha by beta dN average minus alpha nr minus beta es des alpha nr beta es. Okay, now we can compare this with the first law of thermodynamics. How? Now we remember, according to first law of thermodynamics, what we can say is the heat supplied is equal to the energy plus the change in the number of the particles plus delta W. So this is our first law of thermodynamics, and if I say that this quantity B of, comparing these two, B of Q plus N bar alpha plus beta E bar, so D of Q plus N bar alpha plus E bar beta, okay, is equal to beta times delta Q, the heat supplied, where beta being the integrating factor. If we assume that, then we can have the right hand side to be the same. Only thing, you have to compare the coefficients. So beta being the integrating factor for the heat can be assumed to be the inverse of the temperature. We call beta to be equal to 1 by kT, and we can compare these two equations for D of Q plus N bar alpha plus beta E bar. The right hand side can be compared by using the first law of thermodynamics, and you can see the coefficient of D, the average energy, is 1, and we can write mu to be equal to alpha by beta, okay, and dE alpha by, this should be minus mu dN, because the first law of thermodynamics, it should be negative, so this should be equal to minus of alpha by beta, so this should be minus, okay. And then the work done, obviously the work done can be equated with this e to the power minus of alpha nr minus beta es des by summation. So what we can right now understand is beta is 1 by kT, so mu can be written as minus of alpha into kT. Okay, so that gives us alpha to be equal to minus of mu over kT. Okay, so that gives us an expression for the Q, which was assumed to be equal to summation of e to the power minus alpha n, log natural summation of e to the power. So let us try to further interpret Q. What could Q be? From here we can see that Q is nothing but this whole thing Q. So we can write from here this to be equal to, if I write it as, so delta Q by kT. So delta Q by T is nothing but ds, the entropy. So we can write then Q plus N bar alpha plus E bar beta to be equal to ds by k, because dq by t is ds, the change in entropy. So we can write this as S by K. We can equate Q with entropy in this fashion from this particular equation, as you can see. Okay, so Q would be equal to S by K minus N bar, and what is alpha? This is equal to minus of mu by kT, and what is beta? Minus of E by kT. So one can write this to be equal to Ts plus n bar mu minus E bar by kT, and n bar mu is nothing but the gives free energy, so we can write Ts minus E bar plus G, the gives free energy. This is G by kT. So G is nothing but A plus PV, which is equal to E minus Ts plus PV. So Ts minus E plus E minus Ts plus PV by kT. So this cancels out, this cancels out, and this Q is nothing but equal to PV by kT, and this is the basic relation or link between the thermodynamics and statistics of grand canonical ensemble. So we can say that this equation is the link between grand canonical ensemble and thermodynamics. Okay. This is going to help us in solving different problems. We can further try to emphasize on Q, and that can be done in this fashion. Okay. Q was equal to summation, or sorry, log natural. Okay, there was a log natural factor of summation of Rs e to the power minus alpha nr minus beta es, and we have seen that alpha is mu by kT, so we can write this as ln of summation of e to the power alpha is minus mu by kT, so this would be equal to mu nr by kT, and e to the power minus es by kT. Okay. Now this part, the second part, is the partition function in the canonical ensemble, so we can segregate the summation over Rns because this is over, so we can write this as equal to, let's say, let z is equal to e to the power mu by kT. Okay, and we remember the partition function q nr to be equal to summation over s e to the power minus beta es. Okay, beta es e to the power minus of beta of es. That was the partition function which we remember for canonical partition function. So what we can do is we can write this q to be equal to something like ln of z to the power nr, and now this is only for nr. Summation is broken between, they are segregated, so nr 0 to infinity, they can have any value, multiplied by q of nr, where q of nr is summation over s e to the power minus beta es. So this can be called as the new definition for partition function, and this is the grand canonical partition function, which can be written as a function of z v t, where z is again defined in terms of mu, so we can also write this to be a partition function in terms of mu, v and t. So this is something which would be the starting point for grand canonical partition function, the prescription for calculation of the partition function, grand canonical partition function. and this would be the starting point for dealing with any problem in grand canonical ensemble theory.